some considerations for algorithmic thinking and algorithm knowledge in marketing and how they are applied. So first off, here's a starting question. Why do online platforms need algorithms? And can you think of any reasons for this? Why do platforms like Google and Facebook need algorithms?
To understand what advertise to
Yeah,
the audience.
for example, that's one use case. So there are several use cases, both on the end user side, so consumer side, and then on the business side, which is the advertiser side. So often these platforms are two-sided platforms or two-sided markets, so they combine or connect advertisers with consumers. But on both of the sides, they have their own needs for algorithms. So in news feeds like TikTok, Instagram, Facebook, to select the content that is being displayed, there are algorithms being used there for filtering the possible content that you could see, because it's always more than what you will see. So you will see only a subset of available content at a given time. So that's a filtering problem or a selection problem, how they select the platforms, the candidate posts, or in the case of search, the candidate results that you will see, and then ranking is determining the order of those results or posts, so from most relevant to least relevant, so that they show in some kind of order. So for these these tasks, algorithms are being used by platforms. And then, as mentioned by Maria there, advertising is then on the business side. So basically, everyone who is using Google or Facebook or any of the other social media platforms, those platforms categorize you in groups. So you belong into certain audiences. For example, in Google, Google's classification, they have different types of audiences. For example, in-market audience is a type of audience where if you are buying a car, then you're searching about cars and different information. So given that search history, Google might label you as in market for cars. So then advertisers can select these categories in market categories. For example, there are other audience types as well, but this is an example. So then you would be one of those people seeing the advertisements about cars. And in Facebook, you have interest-based targeting. So you are in interest categories. There are thousands of interest categories. So we actually don't know how many exist, because I'm not sure if anyone knows, because I guess it's constantly in a flux, because new trends emerge, new topics. So then it might become an interest category. This is an interesting question, actually, the taxonomies of these companies, how they create the classification taxonomies, and how many categories exist, and how frequently those categories are being updated. But so this is a tool for targeting when we want to do manual targeting. Nowadays, with machine learning, we'll talk about this a bit later, a lot of the manual targeting has gone away, and now we just let the algorithms of the platform sort of find the people that are most likely or more likely to perform the action that we want. So and then of course matching. So yeah, this with what I mentioned, so that the platform is trying to find people, the right people to given the advertiser, given the ad, and given the objective, so the target action that is we want. For example, conversion is the typical sales conversion is a typical action to optimize for, or event. So then it's trying to find the most likely converters and show those ads to these people. We also have something called contextual targeting, which means that if ads are being shown in a display network of websites, those websites have topics and themes, right? So some website can be about sports, so the content is about sports. So contextual targeting means that then the ad network, for example, Google Display Network, would try to select ads that are also about sports, or let's say it's about baseball, so then baseball related ads, because those would be more likely to be in the interest of the visitors, since they are already showing their interest in baseball by visiting the baseball website. But so that's a little bit different. The contextual requires kind of no understanding of the user, because you are making the matching based on the content of the website. But then this person who visits the website, the baseball website, when he goes to another website, for example, now something totally different, like a news website, he can still see baseball ads. So this would be based on the idea of this user classification that Google has identified the interest being baseball, and then that sort of profiling follows the person as he goes in various websites. And then ad auction, so pricing, how much advertisers pay per click, how much they pay per conversion. Actually, they always pay sort of per impression, but that so every time your ad is shown, you kind of pay because well, you're selected there, and it kind of accumulates a cost. But then the downstream metrics like cost of click, cost per click, and cost per conversion, cost per action, are sort of derivatives of that impression incurring a cost for you. But so how it works is that you have an ad auction system. So there are advertisers that bid, for example, in Google's case, for keywords, and also those keywords are now selected kind of automatically in some campaign modes or campaign types. You are not selecting keywords manually, but actually Google is doing it for you, and it's participating in keywords that in auctions for so every time a person is searching for something, let's say a baseball cap, so then your company, if you're selling that and you're running this automated campaign in Google, then Google thinks, okay, you should be bidding on this keyword for this given user, so we will place a bid, and it also determines how much it will bid. This is quite, sort of magical. So actually behind the scenes, Google is operating the bids of millions of advertisers bidding on each commercial search that shows ads on Google search engine results page. So auctions are taking place simultaneously every second. Like now when we speak, there are tens of thousands of auctions going on. They're all automatic. And now the participants and the bids, how much they bid per visibility on that page is set by algorithms. It's not by any kind of, well, you can still set manual keywords you can select, and you can select maximum bids for them, but that's disappearing. It's becoming rarer and rarer, and let's say the current best practices and most professionals, they either don't do it, or then in addition to that, they run these automated campaigns that are actually in practice often overperforming the manual campaigns. So algorithms have already invaded this a lot of the decision making that used to be done by marketers, and yeah, now it has been automated, and it's kind of hidden behind the scenes. So we sort of still know how it works because we used to do these things manually. So we have an idea of what's happening now, and we have a conceptual understanding that, okay, now it's handled by algorithm. But little bit now when, for example, you are entering the field, so you might not do these things manually, so it might be very difficult for you actually to understand what's going on behind the scene if you have never selected keywords or set bids or chosen manual targeting for in-market audiences, then you don't need to do any of that actually nowadays. If you go start with Google Ads, you can ignore all of that. You don't need to know anything. You just basically select a few things and let it run, and it can work like that nowadays. So, but we are still in a sort of a hybrid era where old digital marketing professionals who started with the manual are kind of combining some campaigns and some choices. They want to keep manual, but then others they automate. I'm just seeing that automation is taking, the algorithms is taking much more weight in the field, and it's really replacing a lot of the stuff that we did. So there won't be much need for this manual work. And then also in the reporting, so attribution, so meaning how many how much of the sales value should be allocated to given channels or campaigns or ads. So this is also being changed. How it used to be calculated often, most typically using the last click attribution. So a channel or campaign that gave the last click, like the person came through that ad or campaign or channel, then and made a purchase, for example, 100 euro, then that 100 euro was allocated to that channel or campaign or ad, depending on what level are we inspecting. But nowadays, it's not like that. Nowadays, that one campaign can have a partial value. So there's a way, for example, Google computes it. I have a slide coming up showing you an example, but it's like nowadays that process is also kind of very different than it used to be, and machine learning is used, or algorithms are used in that process of that. So I have got a couple of examples here. First one is the page rank. So this was the big innovation that put Google on the map. So Larry Page and Sergey Brin in 1998 came up with this PageRank algorithm for organizing information. Back then we had search engines like AltaVista and Yahoo that were not working at all at using the same logic. So this like transformed the search, and then they were PhD students at Stanford, and then they created a company out of it, and they got venture funding, of course, being in the vicinity of Silicon Valley, and then yeah, the rest is history. But yeah, so this kind of basic innovation, and the idea was this is using, we talked about graphs last time, so this is kind of using graph logic and assigning weights based on the reputation of a given website. So this can be sort of automatically computed based on just observed data, like how many pages are linking, and this kind of graph can be computed because if we know how many pages link to another page, we can calculate its value, and then when it's linking somewhere else, it has a different weight value than a page that has fewer links. So the more links something has, the higher votes it gets, and so on. So it kind of self organizes the graph by the fact that the spider can, or the bot can, follow the links and count the links and know the sources and destinations. So those are the nodes. So because the web even back then started to become very big, so initially they organized everything in these manual directories, like Yahoo was a directory, and Alta Vista was also heavily based on directories, so manual creation of content. Maybe it worked when you had like initially in the web, thousands of web pages or hundreds. It's easy to catalog them, but as the size of the web grew to millions and beyond, then manually we cannot anymore create categories and catalog everything. So we need these algorithms that can scan the web and sort of self-organize the information. So this is such of an algorithm that works at scale. And Google's mission was to organize world's information, and this was the initial approach that they chose. And links still play a role in it, but now there are a lot of other ranking factors, and the system of algorithms, or the set of algorithms Google uses, is of course much more complicated, and we'll talk about that in a moment. Here's another example, so from the social media. So then again uses kind of graph theory, but this time the graph is not a connection of web pages, but it's a connection of people, and those people are also organized in a graph. So it's a social network. So social network is something that exists offline. So we all have connections, and the innovation of Facebook was to bring it online, so that we recreated those connections by sending the friend requests, and we are sort of rebuilding our offline social network in a digital environment. So that's the big value of companies like Facebook. But then they had to figure out, okay, people are getting more and more friends. So you have more friends, and then you're following pages, and then companies want to show you ads. So now all of a sudden there are thousands and thousands of posts that we could show you. So which ones should we show you, right? So we cannot just chronologically show you the first ones. That might not be relevant, and maybe you will get bored and you will quickly change the service and not use it. We need to optimize it so that you stay sort of engaged and keep scrolling. So this is the newsfeed ranking problem, and so the edge rank was the initial approach, so that there are you have a set of scores that determine whether, or a given post has a score that's calculated as a factor of how recent the content is. So you have aging factor, how important the content type is. So through this you can, adjusting this type of sort of weight, you can make, for example, videos quickly more important, like throughout all the Facebook users, right? You just turn a knob a little bit, you increase the weight of the video content type, and then boom, all the videos get automatic boost across the millions and billions of Facebook accounts. So that's one. And then affinity, so just the quantified relationship between the source of the post and then you, the person whose relationship with this content we are calculating. So when you factor in such criteria, then you get some kind of quantitative score for each post and each person using the system, and then that score can be used to sort the content, so from highest to lowest, and then the highest score post gets shown on your feed as you scroll. So roughly speaking, it works like this, and this you shouldn't get stuck to these what these specifically are. They specifically nowadays they're very much different, but this is to show you the idea how the logic of these algorithms work, which is that we try to model or capture some relationships that matter for users, right? So content type, how recent it is. People don't want to read news that are 1 week old, for example. So, we try to, this is all based on kind of user understanding and trying to create an algorithm that produces content at a given time that's relevant for the user. So user understanding is behind this, and then always we try to figure out how we quantify that. So sometimes it's easy to quantify, like for example, aging factor, because we know that every timestamp of every post. So it's easy to now come up with a decay factor, just a function that as time goes by, okay, now is time t plus 1, so we know what is t, and the bigger the distance is, the more this content gets penalized. So these kind of things are easy, but some factors might be more complex to calculate, like for example affinity, and it might involve other sub algorithms or calculations, like for example the relationship type. Are you family member, or things like how frequently did you communicate with this person in the past, how frequently did you publicly communicate, how frequently did you privately communicate, and so on and so on. So the design of these algorithms is based on user understanding, so that requires some kind of understanding of psychology and what people deem relevant, and then sort of the math and the algorithmic side of it, like how do we quantify, because in the end algorithm needs to output a score. So it always outputs a score, whether it's like the list of possible web pages to show, the list of possible social media posts to show, or the list of products to show. It's always based on a score, and usually that score is like every one of those products or posts has a score between 0 and 1. So that's the usual way how this kind of outputs works, and then it's just ranking from highest to lowest, and that will be the order in the list. So it's not like conceptually extremely difficult to understand, but the magic is then how that score is calculated and what factors we consider in the calculation. And the terminology you hear often in like social media or LinkedIn, for example, people talk about the Google algorithm, the LinkedIn algorithm, like in singular, and that's oversimplification, and it's misleading, because in reality all of these systems are they are systems. They are not one algorithm. So a system has a lot of components, a lot of modules, a lot of stuff it does, and it also has multiple algorithms. Multiple algorithms do different types of smaller tasks, and they contribute to the whole system in some way that the architect or the system designer has designed and planned. So there's not only page rank, there's not only edge rank. Those are one parts of how the whole system works. So it's kind of a funny when you hear this that the LinkedIn algorithm does this and that. Well, there are so many algorithms in LinkedIn. What algorithm are you talking about? And then how do you really know anything? So often people use this verbiage without actually knowing anything about how systems like Google or Facebook or LinkedIn actually work. But they simplify a lot, and then other people are, okay, that makes sense. Maybe it is like that. And then, these kind of folk theories or narratives about how algorithms actually work in marketing become, prominent. Like for a good example is this: don't put links into LinkedIn posts. You need to put them as comments. But that's that's a one like folk theory, but it spreads, and then people start to like follow that kind of behavioral pattern. So all of the systems use a lot of algorithms, hundreds of algorithms, in fact, and then often the outputs are affected by post-processing. So we have also business rules. So if you have a product, you could have a listing, for example, product recommendations that are sorted by relevance for a given customer, and a business rule could then be applied to that list. And the business rule is a hard rule. It would say that if the margin of the product is less than 10%, do not recommend it. So then that list would change accordingly, right? So an algorithm might not necessarily always incorporate hard business rules when it's doing the calculation, but then in the pre-processing stage before the list of items is shown, it can still be altered by hard business rules. So what is now the algorithm? The one doing the computation, or the whole thing that's also including the business rule, right? Because that also affects the output. So that is to say that, again, these are systems that combine some machine learning models, some automated scripts, and some business rules that run according to some business logic that we think that, for example, we should not promote low margin products. And just keep this in mind, that the reality is always more complex, and it's not just a simple and single algorithm that dictates how LinkedIn works or Google works or whatever system works. So they use many algorithms. Here is an example from of what type of systems or algorithms work together with Google. So you have crawlers that crawl, parsers that parse. So you need a parsing algorithm, you need an indexing algorithm that might include, again, sub-algorithms. Then you have ranking. That ranking definitely uses a lot of different algorithms and models to work. And then, a lot of, even when you get the input, the search query, you need to process it. You can have nowadays multiple modalities. Each of them, the pre-processing of that includes algorithms. And so it is it's a combination of algorithms, not just the algorithm that runs Google. There's no such thing. And this, an organization wide, then you have a company like Google with 10,000 engineers all working on a specific part of this picture. So some might just focus on taking the input and improving, making it faster, more efficient, and more compatible with different modalities. And they might have no clue what's happening here on the other side of the big picture. So there are very few people who understand the whole picture, even inside organizations like Google. And here's actually a paper from Google researchers that's quite famous among the machine learning community. So it kind of visually illustrates the idea that even the role of machine learning and AI that we speak and hear so much about is actually quite small when it comes to engineering these systems that use machine learning. So this here visually the machine learning code is very small part of the code base when it comes to the whole system that uses machine learning. For example, Google. This could be Google or similar organization that's running a large scale web service. So it has a lot of other components, and most of the engineering work goes to the other components and trying to make everything work as fast and efficiently as possible. So yeah, even though we have this course AI and ML, so then in production, the role of the AI and machine learning when it comes to engineering the systems is smaller, because once the model is there, then of course in learning cycle 6, uh, machine learning in production, you will have content about that, those production stage challenges, and it doesn't really stop there. So of course this component evolves as well, but a lot of the other components in the system require more engineering effort, or at least when you combine, they require more. So yeah. So when you think of this idea of optimizing for an algorithm, a good rule of thumb is to have this UFO acronym that I heard. It was probably invented by like a friend of mine. I don't know if he invented it, but I heard it from him back in 2009 and Viet Dang. So it kind of stuck with me, and he made sense. So he said it's easy. We just make user friendly optimization, and then that's good search engine optimization we were thinking about at the time. But this applies to any kind of algorithmic system that serves end users. So as long as you're making choices that are consistent with the a positive end user experience, then you are doing things correctly and you're doing good optimization, which is aligned with the algorithm. So actually, this is an interesting twist because now it means that you don't need to know much about how the algorithm works actually to be successful, right? And there are very good cases, sort of. You can see every day, like these influencers, they don't know how TikTok's algorithm works, most of them, and they don't really care. Also, they just produce great content that has, like, viral appeal, and that viral appeal is coming from the fact that they're appealing to human psychology. They're not trying to please the algorithm, they're trying to please the users using the system. But coincidentally, because that's the same goal for the algorithm, it's trying to find the content that has better addictive power. So then, if you are able to produce such content, will organically rise in the ranks of the system. So the algorithm puts you higher, but you don't need to know how the algorithm does the computation and calculation. What you need to know is how to create content that appeals to human psychology. So you should be studying the human and not the algorithm, right? So this is sort of a completely different approach than spending a lot of time studying the algorithms and trying to figure out how they intrinsically work. That's an area if you want to work in a tech company and want to contribute in like better systems, for example, maybe systems that are less addictive and more ethical, that would be great. So there's also, of course, need for better design of algorithms. So then we need to understand more about how they actually work. But if you are a user, if you're a marketer that wants to gain more prominence for the content, should focus your effort on understanding the users rather than understanding the algorithms. So yeah, we mentioned already application areas, search and social, recommenders or recommendation engines or recommendation systems. These all refer to the same thing, are another very important field of or domain of application for algorithms. We have different recommender types like collaborative filtering. So if people saw this, or people that purchased this product often purchased also these other products, and then so on, or similar people to you tend to purchase like this. So this is basic idea of collaborative filtering. Can have also content-based filtering, which is that this content you like the movie Matrix. Okay, so here are more sci-fi movies because Matrix is a sci-fi movie, sci-fi action movie. So we are finding similar content based on comparing the content attributes. And so recommenders, that's one major area as well for algorithm design and application in marketing. And then you have various optimizers. So when we, for example, talk about the pricing or selecting if like your ad, you created an ad in Google Ads, and then now Google is trying to figure out, is that a good ad? Should it be shown? So they are likely to measure if people click that ad, if they click on that ad. So that's measured by CTR or click-through rate. So how many people saw the ad and clicked. So how do you think Google is determining that? Like, they have millions of ads at any given point in time that are candidates. And then, okay, for a given search query, they might have, you are searching for a restaurant in Vaasa. So maybe there are now 100 advertisers there. So, okay, Vaasa is a bit smaller. Let's say in New York, or let's say Helsinki. Okay, so in Helsinki, you have more advertisers than you have more spaces there in the ad section because you have just room for a few ads in the search engine result page. So how do they select this? So they look at the history of your click-through rate, but how much should they give you impressions to determine if your click-through rate, let's say they show 10 times your ad and you get 2 clicks. So now it's 20% your click-through rate, which is quite high, I have to say. So are they now saying that, okay, your ad is very good, we should show it more? Or what do they do? Like, are they waiting till you get 100 impressions so they get more data, and then now it shows you get 15 clicks, so now it's 15% or should they wait until 300 so they get more statistical representative results, and should they wait for 1 week before determining if that ad is like has a higher probability of being included? So this is type of a like real-time optimization problem, which is different from A/B testing, for example, because we don't have the luxury of we need that ad now, we need those candidates now. We cannot run an A/B test, right? Waiting for 1 week, which ad version is better. And so what we use is optimization algorithms that are more quickly making a determination whether an ad is better or not. So typically multi-armed bandit algorithms that more quickly say that, okay, yeah, it will explore a certain number of times. Let's say you have a candidate ads and it will explore their performance for a while, and then there's a clear winner, it starts showing it more, and then the others will still have a chance and new ads can enter, and that's the ratio between explore and exploit. So maybe we exploit 70% of the time the best at 30% of the time we give chances to the new entrants, and if they start to have a higher CTR based on a small sample of impressions, their rate is increasing, and then they can challenge the best one, and the best one might be replaced, and then the new winner will be the one that's being exploited until it loses its appeal, and then automatically it's again replaced. So this works better when you have a lot of incoming new material, you have a lot of tests you need to do, you can do all that automatically, and it's a big innovation that then works in the ad side. So if PageRank was very successful for Google in organizing the search results, then this type of multi-arm bandit algorithms are very efficient in how they organize the advertising side of things. So yeah, so when we talk about the algorithms, it's very important to remember this garbage in, garbage out idea. So it's like when we select, let's say, when we do actually, so when we do our own machine learning projects, and now forget about the Google, those algorithms are embedded there. We cannot change them. We are just users of those algorithms. But then we have our own machine learning projects, like we want to develop our own classifier to classify, for example, the sentiment, like we did last, or we annotated last time. And this following week we will do the machine learning modeling. By the way, I have to say at this point, I forgot to mention, so Gabriel Franco is giving the workshop on Friday, this week's Friday, so please attend that. So I'm hoping we get more attendance than we usually get, since he's taking his time to to run the workshop and teach you a state-of-the-art thing, which is marketing mix modeling using Cassandra tool. So not many people know how to do it, marketing mix modeling, but it's very important. It's the fastest growing form of digital marketing measurement at the moment because of all the challenges with privacy and GA4 and analytics has a lot of problems, but MMM is one possible solution to those problems. So that's why it's a rising and trending topic. So yeah, please attend. It will be useful for your skills to and your CV to know about MMM. Okay, so so when you develop your own machine learning models, for example, classifiers, then the current algorithms are pretty much always good enough. And so here's sort of a visualization on how algorithms are used in demand generation and in the customer life cycle. So this, I think, is a also quite useful visualization in understanding that in addition to algorithms being used in different systems in different ways, then we can also understand their role as part of the customer journey or customer life cycle. So starting from targeting, bidding, nowadays, especially content content generation using generative AI and so on, into targeting and lead scoring and so on, dynamic pricing, chatbots, predictive customer service, marketing automation to increase customer lifetime value, and so on. So algorithms are kind of can be categorized in different stages of the customer journey. And when we do run machine learning projects and we build classifiers, for example, then we typically compare different algorithms. So we have, for example, here, we have some data, and then we compare the performance of 4 algorithms in this case. So again, this is when you are running your own machine learning projects and not just using the systems that are have some kind of algorithms embedded or built in. So you would select, for example, decision tree, naive Bayes, k-nearest neighbor, support vector machine. So these are typical kind of like basic algorithms. And the previous slide had the point that all of these algorithms are pretty good, right? So their relative performance tends to be quite small. So it's more important to have this data in order. The data has good separability. If the data has good signal, almost any of the current state-of-the-art algorithms, and these can all be implemented very easily by literally just typing one line of code and selecting different algorithms. Well, sometimes some of them might require that the data is processed in some kind of distinct way, which is different from how some other algorithm takes that input. In that case, you need to do a little bit more thinking, but in many cases, they take the input in the same data frame, data structure, pandas, data frame could be inputted and then to get the prediction. So the algorithms use some kind of different logic. So decision tree literally has a tree type of structure. Naive Bayes use the Bayesian mathematics. K-nearest neighbor uses this kind of clustering approach, and then support vector machine uses this support vectors to build like a hyperplane and then calculate the like frontiers or differences between the classes. So and these are just a few examples, but the point is that they sort of solve the same problem using different mathematical and logical foundations. And then given that we have a test set, we can see when we train these classifiers using some training data, we can then compare their performance and we can choose usually the best one, and then we would proceed into hyperparameter optimization, and then we can save that model and we can reuse it whenever we want by inputting new data and getting the predictions. So a couple of things here are that algorithms are always unchanged. So these are kind of like standard algorithms. You can easily use them. You can very easily in scikit-learn, which is is the most well-known machine learning library in Python. You can sort of, they are all built in there. Somebody has programmed them. It's very, very neat, right? So you don't need to you don't need to program your own algorithm. You can just simply select, load from scikit-learn this and that, and then tada, you have that algorithm. So that's why it's very easy to run this kind of experiments with multiple different algorithms and compare them. But the models are unique. So remember that the algorithm that you use, so decision tree always works the same way. It's a decision tree. You will not change its logic. The way it works, it is how it works. But your data is unique. So when you combine the data with the algorithm, you get sort of a unique model. And some of the algorithms are deterministic. So deterministic means that when you input the same data to the same algorithm, you always get the same result. You always get the same predictions. And others are stochastic or non-deterministic. So you get similar results, but you don't get exactly the same. But it often, so these algorithms have some kind of random initialization that little bit tilts the direction. Usually it doesn't change much. Usually the results are still quite consistent, but they're not exactly the same. There are ways to make them same by including this kind of fixed seed value that makes sure that the random initialization of the algorithm always is done in the same way. So then you can get um, uh, the same results every time you run if you use this fixed seed value. But that's sort of a pseudo-deterministic. The algorithm still is not deterministic. You're just sort of forcing it to be deterministic. But yeah, so we would compare multiple algorithms for a given use case. And here's the process of the supervised machine learning process. So we collect data, do the pre-processing, future extraction, missing values, and so on. Kind of what we did in the first practice session. And then we would sample that data set to build a training and test set. So we will split it either randomly or using some other logic. Then we still need to do pre-processing. So at this stage, maybe we do cleaning, actually, it would be more appropriate. But in the pre-processing, we transform the variables into numerical formats so they can be used. And if there is something like too many columns, we can use dimensionality reduction to reduce the number of columns. And then we do the training. Like I said, we would typically select based on the performance the best model and optimize its hyperparameters. So hyperparameter is a value that we can manually select, but hyperparameter optimization involves defining a range of values, and then usually there's another algorithm that then tests the combinations of these values. So for example, in clustering, maybe this is easy to understand, hyperparameter, the most typical hyperparameter is the number of clusters, right? So if you have a data set, that's actually what you decide how many clusters comes out of it. So you can set the hyperparameter value to 2, and it splits the dataset into 2 clusters. So each observation belongs to cluster A or cluster B. If you set it to 3, it does the same. You have 3 now. Cluster A, cluster B, cluster C. Each observation will be in one of those clusters. So you see, it's not like a magic. You can say, oh, tell me how many clusters you have that mirror on the wall, tell how many clusters there are. No, it's not like that. You need to actually test it in a data-driven way. So usually we give a range of cluster values, like from 2 to 15 or whatever. And then actually it does 15 times the clustering. And then we look at some kind of metric to determine which number is the 5 cluster optimal, 6 not 7, 4, 5. So we have some kind of metric to figure out what is the optimal number of clusters. But that's not like us or the algorithm. So it needs something from us, right? So that range of those numbers, and then well, the metric. But so what it needs, the number is the hyperparameter. So models have internal parameters that they use for computation that we cannot touch, but hyperparameters we can adjust. And typically we adjust them by giving multiple candidate values, and then we have some kind of outcome metric that tests which combination of hyperparameter values is optimal. And this can be sort of automated. There are, for example, grid search algorithm in Python that you can implement for that. So then, yeah, post-processing, I mentioned the business rule earlier, but this is more about looking at the results and selecting a model. So usually we select a model, so which algorithm creates the best model given our success score. Like for example, typically F1 score is used for as a performance metric, and then we would have our final model, and we could use it for predicting new data until it doesn't work anymore and we have to retrain. So that would be, do you have any questions about this overall process? So it seems it might be a little bit a lot of information. Okay, if no questions, then I'll continue. Here are some more use cases for AI and machine learning in marketing. A recap. I found this infograph or infographic, and it looked pretty good. It's a little bit older. It's from 2019, but still valid. So recommendation engines would be one case where algorithms are implemented, and we discussed those already. Second is forecasting. So in forecasting, use historical data, and in forecasting, usually we predict a numerical value. So sales forecasting is the typical use case, and this would be a regression task in machine learning. Addressing churn is another, let's say, classical or typical way of using algorithms in marketing. So churn means customers that are about to leave or leave. So from business point of view, we want to predict if someone is at risk of leaving us, especially when we have a software subscription business. For example, software as a service, like if you have Netflix subscription, that's a service-based model, subscription-based model, or telephone, mobile phone operator, and so on. So in many these type of businesses, they want to keep you as a customer, of course, so that you generate consistently revenue to them, and they can maximize the lifetime value they get out of you. So churn prediction could be trying to develop a model and then run it on a continuous basis. For example, every day, every week, or something like that on every customer. And again, you get some kind of score. So if your score hits that a certain number, you are classified as at risk. So yeah, we need historical data, of course, on customer attributes and behaviors, whatever are the features. But then given that's accurate, then we can say that, okay, here's a list of these 100 people are now at risk of leaving us according to machine learning. So please call them and ask if they are okay and if we can do something to improve our service, right? So this would be a good use case for machine learning. Content generation, even back in 2019, they mentioned this as a use case. The NLP technologies for content generation were very, very weak just 5 years ago. Now they are extremely strong with generative AI. So this has really become a mainstream use case. Can algorithm be integrated in Salesforce? Yeah, so Salesforce uses a lot of algorithms, like I mentioned previously. I don't know how many they use, but they use hundreds of algorithms for sure. So each algorithm is a different. So Salesforce uses a lot of algorithms. It's actually nothing else except algorithms and bunch of other systems that get things done. Then I'm not sure what the question is about. Maybe on to little bit give more context why you're asking this, but CRM uses algorithms. Customer relationship management uses I mean, you can use algorithms, depends on the use case. You have to be more specific. CRM is a database of customer information. Then what you do with that can make use of algorithms or cannot, depends on like if you use it. You can build from customer information various models. You need to have some kind of, let's say, dependent variable that you want to predict. So if you have customer relationship management data on something, like for the churn case, you would use CRM data. So you have historical information about people who stayed loyal for a period of time, and then who didn't stay loyal in the same time, right? So you have these rows, and then you have columns and age, gender, frequency of usage, whatever are those features, and then they have the target variable stayed loyal for at least 2 years. 0 didn't, or 1 did. So now you have those two classes. You can train a classifier and then apply it to the new or the current customers to get a prediction. Oh, okay, now these are likely to be categorized in the non-loyal group, so they are at risk. So this is one way of implementing it. But yeah, I'm not sure if I answered the question there, but algorithms are already in Salesforce. Salesforce is all about algorithms and so on. So and also algorithms are in other systems, like I mentioned in Google. So hyper-targeted advertising is kind of like an odd term. I haven't heard this hyper-targeted, but algorithms in targeting are used. That's a very typical use case. So Google Ads uses and Facebook and TikTok ads, X ads, and all. They all use algorithms for targeting, and the same with the pricing. So pricing, I previously mentioned the example of pricing the ad impressions in the auction system, but also we can price products by predicting if we have some information about people when we display the product. Every time we have some information to make the prediction, because here if we have this new data, the new data has to have the same information as in our test data. So if we train a model and we know, and factors are, for example, age, gender, frequency of usage, then for the new data to make the prediction, we have to have always age, gender, frequency of usage, right? So it needs to match, the structure of the data needs to match the training set. Otherwise, the model doesn't have the, so we cannot predict something that's not consistent with the data structure that the model was trained on. So this can be an issue, because we need to make sure that whatever data, whatever features we use for model training are also available in the new data. If they're not available, we cannot make the prediction. It needs to be consistent. That's an important point. And then, yeah, scoring, lead scoring is one thing. So that's in B2B. So how likely it's costly to contact, it's costly to run B2B sales force. So then how likely lead will convert. So this would be, we would, for example, use company information to categorize them and try to choose the companies that are most likely to convert into our customers and then contact them first. So this would be a supporting analysis for manual sales operations. Marketing attribution, yeah, I mentioned already the idea of data-driven attribution, so that we use machine learning to. Machine learning is used, well, let's say algorithms are used for computing the attribution based on the information that Google has, but machine learning can be used to fill in the blanks as well. So if there's, think of the modern customer journey now, we don't necessarily know all your full journey, like all the touch points. But if there is enough similarity between you and another person and in your kind of outcome result of buying a product, then we might try to predict that, okay, some touch point that we didn't capture, you have a higher probability of actually having taken that touch point, we just weren't able to capture it. So this could be one way of using machine learning. Yeah, Valid is posting something there about Cypherbot. So yeah, so the targeting use case is kind of like this. So human, I think this slide is really good. It's from I think a presentation from this company Smartly. So the idea is that we have two ways of target, right? The human and then the machine learning. So this is, I think, very, very good illustration, because here we have the idea that the human, when we do the targeting, we apply a lot of our, let's say, biases and stereotypes who our customer is. Often we don't know, that's just an idealized version of it. And then we use those criteria, oh yeah, it's male, 45 and Helsinki, but that narrows down a lot of the opportunity space. So we exclude a lot of potentials here. So then we then in an like automated system, what happens is that, for example, Google Ads or Facebook tries to create subgroups and subgroups and subgroups to find the best combination of customers, right? But if we narrow this down already as humans, it will have less room for testing. All of this white space here is also possible uh, population, for example, in Helsinki. But we are not testing it because the marketer said that that's only males 45-year-olds. So if the marketer was right, then this is good, because we are not wasting any money here testing on the other target group. Some products maybe are only for male 45. In that case, it's very, very good. But in other cases, we might have general product that also could be purchased by female 25-year-old. So then in that case, we would lose out and the algorithm cannot really test. So the other idea is the current, let's say, mainstream in targeting when it comes to online advertising, is that the groups are very big. So we keep them very big. Facebook gives a recommendation 2 million people. Have 2 million people in your group. Of course, in Finland we cannot do, and that recommendation is for the US. But it kind of shows the idea that they want a big group, and they want to have the freedom to do the exploration and the grouping. So they will build those groups, and they will show maybe, you know, the ad, 30 times for a given combination. If it doesn't work at all, they stop showing, and then they again 50 times to another. And then, yeah, this is the logic of the greedy optimization, that then they focus on the groups that actually give positive response, and then they forget about the rest. So again, this can be done automatically by algorithm, but it will be interesting. It's an interesting thing now, how human can bring value in this process, because we might actually hamper our manual targeting might hamper the working the performance. It would be better if we did nothing and just let it, in some cases. So if we are right in our narrowing down the audience, it's good. We can save cost, fewer wasted impressions. So this is good for the platform. It's good for us. And also, if we have a better hunch, that it might be these people, but I don't know exactly what, then that's also useful, because by narrowing down, we can give the algorithm a more precise space to explore further. And also, when we are doing the targeting, we can have we have idea of, like, customer persona in our minds. So, okay, this male 45 Helsinki, we can write a more compelling message to them than if we are just thinking all people in Helsinki. It becomes, we need to balance our communication more, and we might speak to them differently, which might, more specific way of communication style might work better. So that's one possible advantage. On the other hand, we might have biases, we might be wrong, and if we choose totally the wrong targeting, everything is wrong. The machine, the algorithm is not able to find a working combination there. Our quality score will go down, our click prices will go up, everything is looking very, very bad because we made the wrong guess there. And also, even though, let's say that male 45, Helsinki would be optimal target group, but let's say for that same product, it's a very competitive group. So let's say male 45 in Turku would now be much more lucrative, but they could still buy our product. So we would have the best group, yeah, but it's more competitive. So actually we are sort of losing money. So now again, our narrowing down is making making the performance to be suboptimal. And also in some cases, if it very narrowly target the group, like let's say it's now 5,000 people, or there's a certain minimum under which you cannot go in those targeting platforms, and they show you actually in real time the audience size, for example, in Meta ads or Google ads. So they show that, for example, 100,050 people. And then if you make further narrowing down, okay, it goes down to 100,000. Okay, it went down to 50,000. So the idea is, if it goes down too much, that will like, here is the logic of machine learning, that you need certain number of impressions and certain number of people and groups for the algorithm to learn some robust associations. So if it's too small group, it's not able to learn enough. So it cannot actually improve the performance. So that's another sort of argument for bigger audiences and bigger target groups when we run on advertising. But there's a counter argument to that, which is, again, some products are naturally limited by their properties, right? So when you're selling Rolex, for example, um, you shouldn't target the general population. They don't have money for Rolex. But the hard part is, can you narrow down the thing? So the question is, can Facebook find the Rolex people, or the potential candidate for Rolex, more efficiently than human targeters? That's the question. So this is an interesting thing. Sometimes humans might. So here's an example: income criterion, net worth criterion, home value targeting criterion in Facebook ads, and then interests. So it seems like a convincing profile that this person is trying to build for the targeting. So, if we build such smaller micro audiences, are we now saving a lot of money, because it doesn't need to start going through the whole London to find these people. We already told that these are the ones we want. So there is a trade-off, and it's not like completely lost for human targeting yet. So here's a comparison between the bandits and A/B testing. I mentioned earlier that this multi-armed bandit logic is very important in marketing use cases and in like this optimization of advertisement, for example. So in brief, it's we call these algorithms epsilon greedy. So epsilon would be the hyperparameter. Remember what hyperparameter means? It means a value we can set. So what does it mean here? What is the epsilon? Epsilon means the ratio between the explore and exploit, right? So if the epsilon is we set it to 0.2, so then it will explore 20% of the time and exploit 80% of the time, or it might be vice versa. But anyway, we set it to some value. We have to figure out how it exactly is. If it's 0.8, we need to set, so then that epsilon is means that we exploit 80%. So it is a value, and then we set it. So then it means that this algorithm uses the best known option 80% of the time, and 20% of the time it randomly tests other ad versions, for example. So this is like the logic is similar. A good example is in Google Ads, you have campaigns, and under campaigns you have ad groups, and ad groups have ads. So you can add before you could add any number of ads. Now it's called responsive search ads. So you can add no more than 3 actually. Before you could add like 20 or 30, 50, whatever number you wanted. There was maybe some kind of maximum, but that was in the thousands, and so it's pretty much a theoretical maximum. But anyway, so now it's not anymore. Now it's still okay. You have those 3, so it's sort of selecting out of those 3 which ad to show. But it's now a little bit more complex because each ad actually has a certain number of headlines, and it has short headlines and long headlines. So you might have 3 short headlines, 3 long headlines, and then 2 descriptions, for example. So that makes the anatomy of the search ad, the text ad that you see. So what Google is forcing you to do now is to give its raw material. So you need to write 5. You're not writing 1 ad. You're now writing 5 headlines, 5 long headlines which are longer, and then you write 2 descriptions, which is the body text of the ad, right? So now you have these components, but okay, the logic is the same. Now it's taking the combinations, which uh, short headline it should combine with which long headline and which description, right? So we have these possible combinations there. So it goes and takes those combinations and it tests it. So the best combination it can use after it gives all of them maybe, let's say, I don't know, 30 impressions or whatever. And then, okay, it already chooses one, got a click, ding, it's the best one. It continues not testing, and the others still get impressions. They keep getting impressions, but unless their target metric, like for example CTR, um, outperforms the top one, the top one will combination will always be shown. So the idea here is that we get, so on the right here, on the right side figure, we get quicker to the better results than in traditional A/B testing. Traditional A/B testing, and here we have ABC testing with 3 options. So, but we run all of them for a certain period of time. In this example, 5 weeks, and then we choose that option A worked the best. So now we're gonna use it all the time. So we get the maximum value. But we sort of lost 5 weeks with this B and C that clearly outperform. So the bandit or the epsilon greedy algorithm will make us more quickly find this option A. So it will start diminishing the ratio of or the number of impressions that this option C and B get much more quickly. And by the end of 6 weeks, they're hardly at all shown. Where this example is not entirely compatible with the 20% because 20% of the time they would always be something would be shown from the worst ones as well. But yeah, this is a powerful thing because it's kind of works in an automated way. You don't need to manually say that I want to use option A. Like in A/B testing, that's what you typically do. A human takes a look at the results. A human goes, okay, I will pause B and C ads and I will just run the A ad. But here with the algorithm, this multi-arm band algorithm, it's automatically doing everything. So there are hyperparameters we set, like for example, how many, what is this ratio, this epsilon, this explore exploit ratio, but other than that, it works automatically. So this is why it's used, because you can use it at scale to make multiple like decisions kind of automatically. Any questions about this? All right, moving on. Then we have this data-driven attribution. I mentioned earlier that we have a slide about it that shows how it's working. It's based on these Shapley values, which is a concept from economics, game theory. That is basically, it's a formula to calculate how much some in marketing case, how much some channel or touch point contributes to a conversion, contributes to an outcome. So I think this example from Google is really good at explaining this. So we have two paths because Google has information about what we did. So in this case, two people had the same or let's say groups of people, because these paths involve a lot of people because Google has a lot of information and there are like similarity patterns. So someone is looking for best tech gifts, then goes to also searches top rated phones and Google Pixel 4, and here has ad exposure. And here they do basically the same, but they don't have ad exposure. So the difference between these can now be used to calculate how much this ad exposure brought incremental impact. So this is a way to sort of try to simulate the case in which we didn't have this ad exposure. Yeah, this specific ad exposure with Google Pixel 4. So this is not this is similar logic now to A/B testing, because we are trying to compare against the control group, but these are synthetic controls that we are building here. This case of no ad exposure is a group of people that were in a similar path, but they didn't have that intervention, which is the Pixel 4 ad exposure. But we can observe these groups' conversion probability also. So we have conversion tracking installed, so we can see the outcomes for both of the groups, and then we know the intervention was administered to only another group. So this is sort of also now being done at scale automatically. So this is a very different way of like using algorithms for attribution modeling than what existed just a few years ago. So this has kind of actually improved Google's numbers. So this is now problem for the industry is a different thing, because now they're doing a sort of estimating. They're estimating the impact based on kind of this estimation has some kind of error and possible problem there. There could be a lot of problems in this approach because we are building synthetic controls, and that's not really necessarily a robust way to show causality and so on. But this will outcome a number now for your campaigns, that and the conversion number of conversions can now be, it used to be like, let's say 15, so that's a number. Now it can be something like 18.7, and you're wondering, what, 18.7? How can it be a point something, because there should be a clear number of like 15 purchases. Now it's 18.7. What does it mean? So it's coming from this calculation, because the calculation doesn't return full numbers. It doesn't return integers, but it returns a decimal value. So that's your new number of conversions, right? So it now requires us to also rethink it a bit. So at least they showed that, and they didn't round it up or down to give you kind of a unrealistic impression of it actually being the number of conversions. So we don't know anymore what the number of conversions was. Now we have this estimate, which is called data-driven attribution. A lot of the marketers really don't know about this, and they don't care about this. Google told them to use data-driven attribution. That's what they're doing. It gives great results. They can report to their boss, or if they're advertising agency, they can report to their clients. You know, everyone wins, right? And the client is happy. Oh yeah, Google bringing us all this money. And yeah, part of it might be inflated. We really don't know. There is very little independent research into this accuracy of this data-driven attribution. And the whole thing, you know, the concept of accuracy is very difficult in the context of attribution, because we really don't know what is the truth, how much something affected something. It's always kind of a guess, because you know, even people cannot tell you how much did I saw this ad, I clicked it, how much did it affect my decision. There's absolutely no objective scientific method of knowing it. So, you know, mm, this is an educated guess. Maybe it is a good one. And anyway, it's being used now. So data-driven attribution has totally taken over. So that's the default attribution model nowadays. We can forget about all the other attribution models, especially when running Google Ads, which is the dominant platform. So it is here, whether we like it or not. And here's an example of a smart display campaigns idea. So smart display campaign is one implementation of machine learning algorithms in Google Ads. There are others as well, but so basically the idea is that we set what do we do as advertisers? We set a target. So here is cost per click, but often it's target ROAS. So target return on ad spend, how many euros we would like to be returned for every euro spent is a good. So if our ROAS is 400 or 4, then it means we want 4 euros back for every euro we spend. And then we give a campaign budget, how much we want to spend per day. And then we give some creative assets, like I just described, that Google is making us write 5 headlines and 5 long headlines, and then 2 long descriptions and something like that. So then it's going to do everything else for us. So it will give us specific places, locations, websites where the ads are shown. We don't choose. We can select some kind of brand safety settings, but Other than that, it would choose how much to bid in the ad auction for every given user that's um, a candidate for seeing the ads, and then it will build the advertisement. So responsive ad means that it's combining freely the assets that we give. We give images, we upload. Currently, I believe it's 20 images we can upload, and then we can upload also videos, and then, like I said, we write those headlines. It's building that responsibly, and it means that the mobile version might look a little bit different because we upload images in different dimensions. The desktop version, tablet version look a little bit different. The version for TV, so a lot of the ads are shown now in YouTube, so Google is showing them on TV as well. So bigger screens affect what kind of assets it will use, and also the performance of the assets, like how well those texts that we wrote seem to perform. Then it picks the picks the ones it finds are performing the best. So a lot of this is now truly automated using various algorithms. And one interesting side to this was actually by a LinkedIn post by Santeri Salonen, and Santeri is coming to give guest lecture, so remember to be present when he's coming. But what he basically wrote in, here's the text, you can read it. What he basically said was that actually it doesn't, from a machine learning point of view, whether we give a target of, whether we call our target sales or traffic or number of visitors or number of engagement, it absolutely doesn't matter. For the algorithm, it's just a number to optimize. So that was, I think that was pretty insightful. If you understand that, you kind of understand how machine learning is integrated in these models. So it doesn't, all the algorithm there does is it sees a target number, and that number it's labeled by us. We give it you know the meaning of it, that it's sales or it's visitors or it's number of engagement. But algorithm doesn't care at all. It sees a target number, it has some features, it tries to find the association. That's all it does. So it's sort of like interesting then that we could input actually anything in our conversion tracking, and if that makes more sense than the actual thing they say, like sales, instead of sales we could input actually our own lifetime value prediction, and then Google's algorithm would try to optimize for that. Even though we chose in the ad platform's UI, we said this is sales conversion value. So like it would work because they don't they just want a number. So we can give them any number. If lifetime value would make more sense for us, then we could give that and it would work, actually, the optimization. And now it would optimize for lifetime value and not for the conversion value. But it could be configured as because it's us, our website, that pushes back that value to Google's system. So that's kind of interesting. And then this is vital part from a marketer's point of view, is you need to start thinking in terms of, if you are going to machine learning development, model development, you need to develop a skill to translate a marketing problem into a machine learning problem. So for example, this you want to categorize customer feedback as positive or negative. What machine learning task is this? I could ask this in the exam. Like, this would be great exam questions. So what would you say? Sounds like you need to use Cypher, but for this, if you still don't know, at this point you should know Yes, it is classification task. Good, Levi. But what type of classification task? And actually, the answer is it can be we can use a lot of different names for this actually. So the classification is correct. What type of classification? Oh, it cannot be clustering because you have positive or negative classes already, so it's supervised learning. This is a supervised learning task. In clustering, you don't have this kind of pre-existing classes. So these are clustering task. Sorry, supervised machine learning task because we have these target classes, positive and negative. It's a classification task because we classify classes, right? We want to predict classes, positive and negative. And since we have two classes, it's a binary classification task. And we could also presume here that customer feedback is in text. So then we would say this is a binary text classification task. So we try to predict two classes using text as our features. Good. And then you want to predict how a given add text performs. So what kind of task is this? Stars, positive, negative. That doesn't matter for it's still not a clustering task. If you have, no, this, yeah, I just, no, sorry, I don't understand the starting, but you have a customer feedback, some text, and then you want to classify it positive and negative. You do labeling like we did last Friday, and then you develop a supervised machine learning model. So that's it. So the add text prediction, how well it performs. So here we would need historical data. First of all, we need to define what performs means. So we would need historical data on ads and some performance metric, for example, click-through rate or CTR. So we would have 100 ads or 500 ads or 1 million ads that have a CTR, so click-through rate, for example, 5.2%, 3.7%, and so on and so on. So now what type of task is this? Oh yeah, guys, you will struggle in the exam because these are the easiest questions in the exam. Now you need to really start looking at the lecture notes and talking to CipherBot because this is from the basic. This is a regression task. It's a supervised machine learning task. Regression. We want to predict a number, CTR, for example. So we choose what metric we want to predict. CTR is one. We could have conversion rate, we could have conversion value. As long as we have historical data on those, one at a time we can predict. We cannot predict all of them at a time. So we can develop one classifier to predict CTR, one classifier to predict conversion rate, one classifier to predict conversion value. Yeah, but it's supervised machine learning task, regression. You want to segment your customers. What task is this? Here we go. Good, Ahmed. This is clustering task. Good, Olga, you got it. So it's an unsupervised machine learning task and a typical example of clustering task. Correct. Good. And remember, so I included here this mention that algorithms are embedded in all of the systems we use. For example, in Google Ads, they kind of work there in the background to do stuff. And then the other part of using algorithms is actually us developing our own models for things like sentiment classification or ad text performance. We don't necessarily, this might not be, this ad text performance might not be even relevant because we don't need to really know about what works, because we just can create a lot of different versions and then Google will figure it out. This is kind of like the paradigm. But there are still cases where we would want to automatically categorize, label data. We have a lot of comments, a lot of feedback from customers. That would be a typical example. Oh, this customer segmentation, uh, what attributes are sort of what types of customers do we have? So that's one thing. Okay, so Olga, if you have a problem with that Cypherbot, you can send me a message via email. Okay, so we still have cases where we need to, or we can benefit from machine learning using our own data and developing our own models to learn something about customers or to predict something that is sort of outside the online ad platforms. So those are kind of two different ones. In online ad platforms, we don't usually do anything. We just use the algorithms, or we use the system features that run on algorithms. When we work on our own data, when we want to predict customer lifetime value, categorize customer feedback, whatever data we have, and we want to automatically process it at scale, then we develop our own models. We cannot use the online ad platforms for those anymore. So those are a little bit the main different areas or domains of algorithms for marketing. And here are these are just a sort of repetition of what is regression classification and what type of classification tasks are. Those are expected to be in the exam. And here is a visualization of it, of different machine learning types. You can see, if you learn about machine learning, these are the types of diagrams you see. I would say that semi-supervised learning and reinforcement learning are kind of often not relevant for marketing. Most of the stuff we do is here supervised learning or unsupervised learning. I've never done semi-supervised learning myself, never had the need for it. And reinforcement learning would be something, the typical use case is a driverless car. So if you go with that kind of systems or robotics is something where they apply reinforcement learning. It says here optimized marketing, but no, really, it's very rare to see reinforcement learning in a marketing use case. Most of it supervised learning and unsupervised learning are the areas. Here's an algorithm cheat sheet I included from Microsoft. This you can check it out. It's it's kind of complex, but it has, I think, good pointers to learn more about, and it's a good organization of different algorithms into like categories. So you have multi-class classification, binary classification, image classification, regression, text analytics. So different techniques and algorithms mentioned here. So if you're interested, you can look into that more. I won't be asking detailed questions about this, but it's more for your learning if you want to learn more. So the thing with the algorithms is that we don't really need hundreds of them. There was a very good paper back in 2006 about, do we need hundreds of classifiers to solve real world problems? And no, we don't. Their performance, given the dataset qualities, like standard, then the performance of the algorithms has a smaller impact than the dataset quality. So dataset quality is the number one um, uh, uh, key thing when we train machine learning algorithm. Yeah, also important factors are implementability, that the algorithm is available. For example, in scikit-learn, that means that it's usually being kind of developed in a stable, up to a stable state, because thousands and thousands of data scientists use this library. So if there are errors in it, there's a probability people would have noticed already. Something, if you do at scale, like scale to millions of cases, that computational complexity of the algorithm is not exceedingly high, and then that it works sort of on a repetitive cases. So there's an interesting idea or a meme that instead of these hundreds of algorithms or tens of algorithms even that we might compare in a given problem to develop a model, XGBoost is all you need. So there's this data scientist who made this in Twitter and LinkedIn at and XGBoost is a powerful one. So it's definitely one of the state-of-the-art algorithms, and you can use it for regression or classification, many different problems, and it works quite well. In the lecture notes, I have also some contrary quotes about this. Somebody saying that CatBoost is much better than XGBoost, but both are kind of boosting algorithms. So these represent kind of state of the art approach. So like, you know, instead of having hundreds now, we just need one. So XGBoost is a good algorithm to know and to apply. It works well with tabular data. Marketing data tends to be tabular data. So this is a good algorithm for that type of data. We can also run ensembles. So we would have multiple algorithms and may all make a class prediction, for example, and then ensemble is just that we take the majority vote. So whatever the majority of the algorithms say is the correct class, we choose. So that's the idea of ensembles. And another thing that affects here is the explainability. So different algorithms vary by how well we can explain the results, like what features caused or contributed to the prediction, right? So the typically deep learning algorithms have high accuracy, but they have worse explainability than some other simpler models. So then if the performance difference is not that big, then we might, in marketing use cases, select algorithms that are more interpretable, because often we need to give some kind of actionable recommendations based on the algorithm's workings. And if we cannot know what features affected the predictions, it will be difficult. We cannot actually say anything that what should we do based on this result. So XGBoost is again quite straightforward to interpret. So again, interpretability is very good. So also low code or no code implementations are making it easier for marketers to by the way, I will go a little bit over today because I want to complete this slides. If you need to go to the next one, you can already drop this class. I mean, when we are hitting 2 p.m. But I want to complete this. You can watch the remainder of the lecture as a recording then. But I'll just keep going until I finish the remaining slides because those are quite, I think, important ones. So we have especially PyCaret is a good example of a low code library, meaning that you don't need to program a lot to run machine learning experiments. So these kind of libraries and tools make it much easier for marketers to run algorithms and develop their own machine learning models. So in this example, for example, 30 different time series forecasters with a single line of code. So that's a really amazing thing. It really saves time because for you to manually even locate those kind of libraries would take a long time. So these kind of tools that kind of group those algorithms and present functions that kind of do a lot of the stuff that you would still need to do manually. If you code it, you need to have a lot of lines, maybe 50 lines of code, but now this is streamlining it. And if you know the functions of and the functions in PyCaret are named also very descriptively. Remember what we talked about descriptive naming in the first practice session. That's very important. It's not only for data sets and data sheets, but also and file names, but also functions. Those functions are named like model or well, this is a variable here, but create model is a function. So it's easy to kind of learn. So documentation is important, and PyCaret is kind of optimized for that. Here's the creator of PyCaret. So yeah, it's some of the logic of running PyCaret. So PyCaret is part of the AutoML movement, so automated machine learning. And these kind of tools, like I said, make it very easy to uh, develop models, evaluate models, and then deploy models. So something like, the functions here, get data, set up, compare models, create model, tune model, plot, evaluate, finalize, predict, and save and load. These are similar functions that you would see in scikit-learn, but a tool or a library like PyCaret makes it even a bit more, even a bit simpler still than in using scikit-learn. But one thing you need to be cautious about though is that when you use these models, and even easier version is to generate code using ChatGPT, like we did last time in the practice session, right? So we generated some code using ChatGPT. Is it good or not to do that? It's actually good when you know what you're doing. If you don't know what you're doing, it's bad. That's why you need to learn some basic fundamentals. That's why it's good you're taking courses like these. You're watching the videos, you're reading the lecture notes, trying to talk to Cypherbot, trying to understand the machine learning concepts. Because if you don't and you just ask ChatGPT to run the code, and believe me, I've seen multiple times I'm asking it to do something. It gives me a code that works but does the wrong thing. So in machine learning, there are a lot of caveats or like hidden traps where the code might run, but you might have, for example, data leakage or information leakage between training and test set, or you would well, let's put it like this: there are many issues that can possibly arise, even though you would get an output, even though the code would run. It still might be wrong. Then it still might be invalid. So they are great tools once you are able to evaluate the output. This is the same reason why I'm telling all my students not to use ChatGPT for writing, because they need to first learn the skills of writing, right? If you don't know how to write, you really don't know how to think either, because writing is expression of your thoughts. So to make it clear and express yourself clearly, if you don't know that, then how will you cope in the work life? You will not very well, because writing emails yourself is actually a very important skill. You cannot outsource that to a machine, even though Apple and Google are presenting email rewriting as some kind of good use case for AI. It's not at all. But anyway, I'm going off topic. So the point is that you need to know the foundations and the basics to be able to evaluate what these kind of low code, no code systems do. And then accuracy, this is from Andrew Ng, a famous deep learning specialist. 99% of accuracy is game changing, and this has been achieved in a lot of, for example, image recognition problems. The world went from 95% to 99% of accuracy, and really things change. It now becomes something that can be deployed. So this kind of works in the case of factory setup or something where you have very fixed target, right? So I think an example he mentions in the materials that you have in learning cycle 6 will be that you have a conveyor belt with mobile phones, and the machine learning model will read, well, the system will take a picture of the screen, and if the screen has defects, the machine learning model is trying to predict it. So image recognition, so it's comparing it to a model that's trained on phones that have defects, and then if it identifies, it pushes back this result, and then the phone is moved into like further manual inspection or something like that. But that's an easy problem, a lot easier. Even it is nowadays, it's easy problem because that's quite static how those phones look like. But the complexities of the society and consumer behavior and people make this a moving target. A lot of the marketing problems moving targets, right? So for us, it's actually very, very hard to reach 99% accuracy with anything. So yeah, if we get accuracy sometimes in computational social science, which is sort of where marketing belongs, something like 70% accuracy is already, or performance using F1 score is something already that's, we start to look at it possibly useful, and then of course closer to 100 we get, the better. But this is just a sort of like clarification to you that don't compare different tasks from industrial manufacturing or whatever, where the problem is like sort of easier and you're not trying to predict moving targets like in marketing. So don't think that your model is like super weak if you don't get 99% accuracy. In contrast, if you get 99% accuracy in marketing problem, I would first question your model that it's overfitting, that it's just very well suited for your training data, but actually doesn't perform well in the wild. Yeah, marketing involves a lot of issues that are moving targets and a lot of factors that we actually cannot have information on. So if we had perfect information, we could develop a perfect model, but in reality, we cannot. We cannot see inside people's heads, and also, like in this case of attribution, even people themselves, they don't know what is driving their behaviors. So a lot of the problems we deal with don't really have a robust ground truth or gold labels. I mean, we have gold labels and we have ground truth, but if it's really true, is kind of like often debatable. And it means that sometimes we might also not use machine learning. That's again going back to the business rules. Oftentimes these systems use components of machine learning predictions and then some business rule to make a final determination, or then a human in the loop to take the actions and take the decisions. It is very, very important, especially when we are making sort of strategic decisions. So it's always good to have, and if, for example, in Facebook's case, they are flagging sometimes people, they're banning people due to wrong reasons. So algorithm has an error rate. So, imagine they are classifying, hundreds of millions of people. That means thousands of people might be, even with a low error rate, thousands of people might be banned for not a good reason. So if they don't have a human in the loop process, then the algorithm will always say, when you complain about this ban decision, that you are wrong. So this is actually a real case. But it's important to remember that algorithms and models are fallible, and we should have human backups and safety sort of. But yeah, then it comes down to business. Like Facebook doesn't care because over 1 billion users, if some thousands are wrongly banned, it's not worth for them to build manual help desk for people. Nowadays they have this, I guess, if you're verified, you can get help, but you need to pay for this verification. So yeah, that's actually a good example of business development coming out of the idea. People wanted help, so they can get help if they get verified and pay for it. But here's another example where you could develop a classifier for, let's say, a simple problem, but it would take you a lot of time and it would be very cumbersome. Sometimes you can just create a rule and establish or reach the same goal with a lot less sort of effort. So it's important to figure out the boundaries of machine learning where they actually apply. Okay, that's it. So thank you for the attention. And now we can close the session. So have a good week, guys. And please attend the Friday's session so we can, you can learn and we can have a good attendance for Gabriel. Okay, thank you.
Thank you.
Thank you. Bye-bye. See you on Friday.
Bye.